Hello and welcome to Lecture 19, Part 1. Uh, we're breaking up things in class. We've been having our project discussion meetings, but we're still covering details about lecture content. And for example, this is very timely, talking about projects. The second half of this lecture is actually about design space exploration. Once you have your parameterized generator, how are you going to go about encouraging users to set those parameters appropriately? It's a reasonable thing to think about. And of course, power, which obviously is that, third-party PPA. In this part one, we're going to try and cover power and then how much time we have makes sense for design space exploration. When it comes down to it, power is maybe the most important metric for many chip designers. It is the limiting factor for most designs, right? Uh, you can imagine for mobile, of course, the more energy efficient your chip is, the longer battery life can be. Um, and you want to do more. And the reason why you can't do more is not because you have enough hardware to do it, it's because you're going to run out of juice, you're going to run out of power. In a data center, of course, power is extremely important. And have you seen some of the news about some of the newest data centers? Not only are you talking about building nuclear reactors just for the data center, um, the numbers are astronomical, right? So power is the biggest concern. So I already said both power and energy. Let's remind ourselves what the distinction between those things is, right? So power is the rate of energy expenditure, right? So in other words, power over time is energy, or a derivative of energy is power, right? Um, So depending on what you care about really more so energy and power. So for example, things like battery life, it's more about energy, right? How much energy you're consuming over a period of time. Now, you can do things like say, oh, well, I want to run for X hours at this average power. Well, those two things combined together will tell you how much energy you need, right? And so, yeah, energy of course matters. Energy is what you pay for at the utility. It's also what you pay for when you think about battery sizing and how long your battery life is. But power also has concerns. Like I said, power generates heat when you expend that, and so you can make handsets that are too hot. You can have data centers that are too hot. Um, and to deliver power requires a lot of infrastructure to supply that power at a certain voltage and certain characteristics. And so that infrastructure has a cost. If you can make your design have a lower peak power, that actually makes the infrastructure cheaper. Um, and so that's important, not just for heat reasons, but also just power delivery reasons, right? Um, you may or may not have experienced a smartphone that gets too hot in your hand. Uh, Usually, phone designers prevent that, and so let your phone run really fast for a little bit of time, and when it starts to heat up, then it slows it down, so it throttles it, which is a common technique. Additionally, as a hardware designer, of course, think about things like peak power draw, determines the power supply you set. That's cost and size of your device, um, and the average power is kind of your average energy consumption. So these are very broad, basic things. I always include these in the course to make sure we're all on the same page. Questions so far? Okay, so. Um, what can I do as a hardware designer to impact my power consumption, right? Is it the E person's job? No, you actually can get involved. So to first order, that's why it's an approximate sign. Dynamic power P of your design is proportional to this product of four things. Um, Alpha, the activity factor. That is what fraction of the design is toggling. The capacitance, the voltage, and the frequency, right? So in other words, think about it. Forget about, logic operations. Really what your hardware design is doing is it is charging and discharging capacitors, right? That's what it's doing. That's where the power goes. And so you can imagine, yes, if I have more capacitance, i.e., a bigger design, that's going to be more energy flowing around, right? Um, if I do it at a higher voltage, that's also going to take more power. You notice how the voltage is squared. So we probably hear about people talking about, can I figure out ways to reduce the voltage of my design? If you can really reduce the power consumption because the voltage is squared. So it's a really big bang for your buck in that one. The activity factor, that's something you actually control a lot as a designer, right? That's what fraction of design is toggling, right? If your design is clever, it doesn't toggle every piece of design every cycle, right? Some parts are inactive, you put to sleep, you do whatever you need to do. So you shrink down the activity factor. And then finally, the frequency. What clock frequency you're running at, right? If you don't need to go super fast, you can run at a slower frequency. Sure, that saves energy, right? Um, if you need to go fast and you do more things per second, of course, it's going to increase your power consumption too. And so there's a lot of knobs here, right? And they kind of scale differently over time. In general, people make bigger designs in terms of transistor count. Normally, if life is good of Moore's law and stuff, even though the transistor count increases, transistors get smaller their capacitance reduces. So your net capacitance might be similar. Emphasis. Your voltage might slightly go down over time, but then as an architect, you're trying really hard to reduce the activity factor to save energy. Um, but none of these things hold true in the modern era. Sometimes in the modern designs, capacitance isn't shrinking that much, etc. Like I said, so what can you do? Activity, put things to sleep, make design smaller, more efficient. Obviously, take less energy. Great. And yeah, of course, being very deliberate about your critical paths and your frequency and voltage helps you adjust those other parts too. Cool. Questions? Okay. Um, so when it comes to turning things off, what can you do? There's two kinds of ways of turning things off. The big one is literally turning them off fully. It's called power gating, where in other words, you say, you know what, this entire module, this entire component, I know I'm not going to need it. Turn it off at the power supply level, right? So you really turn this thing off. Saves a lot of power. That's great. But of course, the cost is that it takes time to turn it back on, right? When you say, you know what, I want this piece again, it takes time to reinitialize it. And so, depending on what piece you're talking about, power gating may or may not make sense, right? Um, you'd be surprised how some architects and designers are very clever. So, even in your smartphone, for example, because of things like the protocols for your data transition, the cell radios, it knows what times you're supposed to be sending, what times you're not supposed to be sending. So in those idle times, it knows it's going to be idle. It can actually power gate part of that circuitry because it knows it's not going to be used. In that case, because it's very predictable, it knows, okay, I'm send on this time and receive on this time, and then not doing anything in between. It can put to sleep safely knowing when it has time to wake it up. Um, Additionally, there is something called clock gating, which is much more fine grained, and that is recognizing that so on your components of your system, you expend power toggling them when you change the values on wires and logic gates and such and registers. However, if those signals don't change, they won't expend additional dynamic power, right? They may have leakage power, static power, but the dynamic power won't be that bad. However, there's one signal in your design that's always freaking flipping. It flips twice per second. It's the freaking clock, right? Talking all the time. And so as a result, actually cutting off the clock can be a really good power saver. So it's called clock gating, and that is basically you have components, specifically components to receive the clock, which usually are things like registers, and you cut off the connection to the clock temporarily to save power. So you maybe have a clock signal coming in, feeding, let's say, 16 registers. You know you're not going to use those registers, so you turn the clock off higher up, and that 16 endpoints are not being lit up, right? Realize this adds up, right? If you have like a 64 register, that means 64 endpoints you're turning off. 64 times 16, that could be, basically 1,000 bits you're turning off. So um, you can save a lot of power. What's interesting about the clock gating is that modern CAD tools do this really freaking well. And so they can go in and do this. And the only reason why I mentioned in today's lecture is there's a little bit of help you need to give them as a designer. So you might think when you're writing chisel, if you use reg versus reg enable, so reg, of course, is the register. Reg enable allows you to have an explicit enable signal in your register, right? So you think the one to reg enable would be more hardware. In some ways, it is a little more hardware, it has an enable signal. But because you have the enable, that makes it easier to do clock gating, right? Because basically what clock gating is, you need to be able to tell the CAD tools for this time period, I don't care what the value of this register is, and that allows it to do clock gating, turn that register off. In order to make that possible, um, you need to have a register for write enable, and you need to mark the value during certain time periods. Don't care. If you do those things, the CAD tools automatically go in there and do clock gating and does really great things. The bigger the register, the more of these. This helps. And so it sounds really subtle, but when you start power optimizing your design, this stuff really helps. Cool. Questions? Yes. There's a way to write that in Chisel. So it's not the same as the X and Verilog, because the X and Verilog, great question. So the question was, how do you indicate don't care in Chisel? Um, the X and Verilog is kind of annoying because it both indicates, as a designer, I don't care what the value of something is, as well as in hardware, due to nature of simulation, somehow there's a value it can't determine. right? And so that don't care propagation is somehow like those two different concepts that are mapped to the same construct, right? And so Chisel has worked really hard to eliminate both, but really they care more about eliminating the simulation don't care. So the simulation don't care doesn't really exist in Chisel. Like all values are initialized. There's no notion of undefined in simulation. They're randomly initialized. Um, the logic behavior don't care to allow tools to optimize does exist under constrained circumstances. This is one of them. Here I'm using, saying use reg enable. Technically, if you have a regular reg and you have when statements, you can get the same behavior, right? Um, cool. Good questions. Okay. So when it comes to, as an architect, managing the power, you have some choices, right? Um, so let's say you know what you need to do. Like I want to play this video on my phone at 60 frames per second. So okay, I need to decode a frame of video, get that information to the frame buffer to go into the display, and I know I need to do, a frame every 15 milliseconds, whatever it is for my frame rate. So I have, a task and a timeline that needs to occur. Now, if you're trying to do that in the most energy efficient way in order to maximize battery life, there's multiple strategies. And depending on your situation, a different strategy may be the most effective. So one strategy is called race to halt, which is, you know what? I know I have a task that needs to be done. I'm gonna do it as fast as I can. So I'm gonna crank up the power, go into boost, go into turbo, go fast. And as soon as the task is done, put the whole thing to sleep. Turn everything off, and then get woken up the next time for next deadline, next frame, right? So that way you're maximizing the time you're off. Yes. A little bit like driving on a hill. Will be a better analogy. Yeah, actually, a better analogy might be if you're in traffic, if you're driving, and you've all been stop and go traffic, where cars get close, cars get farther apart, and you feel like you're kind of constantly starting and starting. So you have a choice, right? You can basically try to closely follow the person in front of you, and when they stop, you stop, and when they go, you go right away, and then you stop right away. Or you can, what? I'm just gonna mellow out, and it's like try to go the same speed all the time. So this is kind of that trade-off, right? So which one's more energy efficient is actually going to depend, right? So race to halt is you go as fast as you can, and the benefit is the fact that you turned off, right? That's where the energy savings is. Even though you're burning more power here, you turned off here, and that's where the win is. Crawl to deadlines, you know what? I'm going to go just as fast as I need to go to get there, and that can help. And so you can kind of see how this trade-off boils down to is this notion of what's your dynamic power versus static power. That's going to tell you the difference, right? Usually in hardware designs, the first order, you can say the static power is constant-ish when it's on. And so static power is what you pay whenever you're on, regardless of how much static power you're burning, right? So in other words, by turning fully off, you get to save the static power. Now, the price of going fast isn't just you go shorter, you burn dynamic power, right? And like I said, you increase the voltage, you increase the frequency, you crank it. Um, that's going to require more power. So, of course, the question is, which one's less energy, right? And so you're kind of comparing the extra dynamic energy you paid to go faster. Because in theory, by going slower, you're going to burn not just lower absolute power, maybe less energy dynamic power because lower voltage, PV squared F, right? The V squared, lower the voltage, you get a real benefit. So yeah, so the question is this additional dynamic power, energy, so dynamic energy greater or less than the amount of static energy I save by turning off, right? So it's going to depend. So both strategies are commonly used in different systems. So you have these two different approaches. Cool. Um, so yeah, going slow, the same energy, in addition to the race to halt versus crawl a deadline, it's something you kind of want to think about a lot, right? So thinking about just what needs to happen and taking advantage of that, right? And so, uh, as always, try to start from a correct circuit before you start optimizing for performance, right? And then, as a designer, you kind of, especially working your process design team, you're going to figure out how do I set my voltage and frequency to kind of efficiently meet that target, right? So, the crawl deadline is one way of doing that. Um, and like I said, you reduce the voltage, it makes the circuit slower, but also saves power, right? Remember V squared in that term, right? So that's what you're trying to get. And so, you know, for much of your lives using computing devices, you've already taken this for granted, something called DVFS, or dynamic voltage and frequency scaling. Your circuits you operate with, your phone, your computer, they don't just run at one frequency and one voltage, right? They're constantly changing which frequency and voltage they're running at. That's the thing. When they change your frequency, they can change the voltage too to match, right? In other words, let's say a situation where you know you're doing less. I need less performance, so I can lower the frequency. Because the frequency is lower, that means the clock period is longer. So I have more time to get things done. I can slow the circuit down by turning down the voltage. And so, yeah, usually have these DVFS points. Where kind of someone figures out for your chip what is the right voltage or frequency for certain points. You kind of get this curve. You figure out where you want to be at a certain time. Cool. And then the race to halt is the alternative, right? You know what? Let's go fast. Let's sprint through it and then turn off, right? And so if you look through hardware design, it's said that both techniques are common, and you may see both techniques in the same chip. Like I said, so you have these periodic operations very commonly in smartphones. Things like transmitting things on a cell radio, where you have your certain time slot coming up every so many microseconds. You have things like displaying video frames. You'll be amazed how even like on a smartphone, when you think, "Oh, the screen is on, I'm reading a web page," it's going to sleep. Like even the human scale, like things are happening. Even if you're like scrolling your finger and the screen's moving, it's scrolling 100 hertz. 100 hertz, 10 milliseconds, right? That's an eternity in hardware. Things can be put to sleep in that time period. Um, so yeah, so you're always kind of figure out ways to put things to sleep. Cool. Other questions? So I'm going to stop right here.